Good morning, everybody. AP Physics 2. It is hopefully Tuesday, March 24th that you are watching this. Yesterday, you were to have done assignments A and B in Chapter 31, and I hope you've done that. Let me know if you have problems. I know I already heard from Kyle that he couldn't get into YouTube because it's blocked by the school. If that's true for others, I apologize. I have emailed Mr. Cartier and asked him to whitelist this video. We'll see if that happens. Anyway, if you have been able to watch yesterday's video, then you probably have, or else you wouldn't be watching this one. But make sure when you do your homework on a piece of paper that you take a picture of it and email it to me. That way you get the homework credit. We will be going over a couple of those homework problems in this video. In fact, we're going to do that right now. So I'm going to pray and then we'll have class. Lord, thank you for this class, these 9 students. I pray that you will guide them through this day, this week. Help them, Lord, to learn some physics, but especially, Lord, help them to learn to trust you and to not worry, but to walk in faith through this week and through a tough time right now. Amen. All right, are you all here? I trust you are. I'm going to ask you how you did on your homework. And so get that out. If you haven't, get out your homework, assignment A and B, and look over the problems in assignment B, and we'll see how you did. Number 3, I hope was not a problem. You know that protons plus neutrons equal the mass number. And okay, so let me know if you have a question about number 3. We are going to try to do number 11, just as an example of what I taught you in the video yesterday. And then maybe we'll look at one more after that. All right, this is number 11. And I'm going to erase that part of the board to make room for this. So hang on. All right, I need one of you to read number 11. Sophia, would you do that? Read that out loud, please. Number 11. Find the binding energy in mega electron volts for lithium. And it gives you some information about lithium. Li is the symbol, and there is a 7 and a 3 over here. You know what those numbers mean. And then it tells you the atomic mass is 7.016003. That's the mass of one atom of lithium. They want to know the binding energy. So here's what we learned to do yesterday. Let me get the numbers. Sarah, where's my paper? Ah, got it. Never mind. Thanks, Sarah. You need to get the mass defect. You need to find the mass defect, and then you can convert that into energy. Now that's what you learned yesterday. Well, how do I get the mass defect? It's the difference in the mass of the individual particles, and there are 7 of them. 3 protons, 4 neutrons to make 7. And so I would multiply 3 times this number, 1.007825. Now, if you look back at that chart on the first page in chapter 31, this is the mass of a hydrogen atom. It's not the mass of a proton. It's a hydrogen atom. But the hydrogen atom includes protons and electrons. That's why it's a little bit more than the mass of a proton. So this is the mass right here of 1 proton and 1 electron. And there are 3 of each of those. There are 3 protons and 3 electrons. Plus 4 times the mass of a neutron. And the neutron's mass is 1.008665. I believe that's it. So if you add all that up, you've got the mass of the individual parts of the atom, all seven of these particles. And then if you will subtract from that the mass they gave you, which was this, 7.016003, that's the mass of the atom. If you do that, you will get the mass defect, and that comes out to be 0.042132. Now that's the amount of mass that disappeared when these 7 particles turned into an atom, because that's the difference in their masses. Well, that much mass disappeared because it turned into energy to bind the particles together. We call that binding energy. So that energy would be this number, 0.042132 times 931.5, and that comes out to be 39.25 if I keep 4 digits, and that would be mega electron volts. If you use the 931, which is on your constant page of your equation sheet, you would have gotten 39.22. 39.22 mega electron volts. Okay, so that's the answer. That answer, I believe, is the one in the back of your book. This one would have been fine as well. Can you see both of those? There you go. Now that's how you deal with mass defect, and that's how you find binding energy. It's as simple as that. It's just a matter of doing the math. All right, we're going to do one more. Number 15, that's one we're doing next. Use the plot of binding energy per nucleon in figure 31.5. You have to look back in your book for that. So do that now. Turn back to that graph to look at. You'll use that to determine the mass defect for the oxygen nucleus, and then express your answer in kilograms. So what we want is mass defect, but not in U's, in kilograms. Delta M is what we're looking for. All right, now we've got to use that chart. So when I go back to that chart, I see it is here. It's on page 963. It's right there. That's the chart. And oxygen is up in this corner here. And you find it and try to read the graph. When I see the O, and I see a point where the O is, O for oxygen. And it looks to me like it's right on the 8. The y-axis, if you move over from the dot for oxygen, it's on the 8. That means 8 mega electron volts per nucleon. 8 mega electron volts per nucleon. Because that's what it says on the y-axis, that's what it is. Well, how many nucleons are there in an oxygen atom? The O had a 16 up here and an 8 down there. That means 8 protons, but it means 16. There it is. Nucleons, protons plus neutrons, 16. So there are 16 nucleons. I need to take 8 and multiply it by 16, and that will give me something like 100. Here it is, 128 mega electron volts. And that's again 8 mega electron volts per nucleon times 16 nucleons. And that will give you this number of mega electron volts as the binding energy for the entire atom of oxygen. Okay, well, if you know that, what you know is E equals mc squared. Now, we've talked about this yesterday. If this E is in mega electron volts, which it is, and the mass is in U's, then the constant is 931.5. It's not really the speed of light squared, it's this. And so to get U's, that's the mass, you simply divide 128 mega electron volts by 931.5. And when you do that, you will get 0.137 U's, atomic mass units. So all that's left to do is convert that to kilograms, because that was the question, was delta M in kilograms. How do I convert that to kilograms? You divide by, again, I mentioned this yesterday, this number is on the constant page of your equation sheet. You would multiply, not divide, thank you, because what I have is atomic mass units. And if I multiply that, then times 1.66 times 10 to the negative 27th kilograms per U, that's the conversion factor, I will get, the U's cancel, I will get kilograms. And that answer is 2.28 times 10 to the negative 28th kilograms. 2.28 times 10 to the negative 28 kilograms is the answer to number 15. All right. Hope you see how to deal with those numbers in that chart. You see the difference between the atomic mass unit and the kilogram. They're both units for mass. You understand how this equation works when you're dealing with atomic mass units and mega electron volts. You need to know this number, 931.5 or 931. And that's what you learned yesterday, and that's what your homework is about. Okay, we need to learn a new thing today from section 4. And you have read, or will read, I think you will read section 4. So I'm going to teach you some of the basic things today in the rest of this video about radioactivity. So while you're getting your notes ready to write some things down here, hope you're doing okay. Let me know if you need anything, if you're having difficulty with anything I can help you with. I don't know what that would be, but I feel a little off not being able to talk face to face with you. Which reminds me, by the way, starting next week, Monday, I believe it's the 30th, we'll be starting a regular schedule of classes, mostly through Zoom. I had never heard of Zoom a few days ago. I still don't know how it works. I don't know how to set it up yet. But they say they're going to teach me how to set it up. So we will have a Zoom classroom, a class meeting, at least twice next week. And I think all of your classes are trying to set up something like that. Anyway, you'll hear more about that as we get closer to it. But in that Zoom meeting, I'll be able to actually talk with you and you with each other, and it'll be kind of fun. If it works. I have no faith, no confidence, I should say. I have some faith. I have no confidence that technology is really going to work. Okay, come on. Hey, do you remember seeing this yesterday, this picture where I showed you the blue dots represent stability? If the number of protons and the number of neutrons would graph along those blue dots, that atom is stable. Anywhere else, it's likely to be unstable. And I mentioned that neutrons, for the larger atoms, more neutrons tends to bring more stability. And the unstable ones are the ones that don't have the right ratio of protons to neutrons. And so with that in mind, stability is an important concept when we begin talking about radioactivity, which is what we're really talking about today. Those atoms that are unstable, they're not along the blue dots, are radioactive, which means they emit particles and energy in order to try to become stable. All the atom wants is some stability. Isn't that what we all want? Oh my goodness. We want to be stable. We don't want to always be crazy. Well, radioactive substances are not stable, so they emit particles. Things come flying out of them because they're so unstable. Yeah. Well, what are those things that come flying out of the nucleus of an atom that lacks stability? There are three things, and I bet you know what they are. We actually talked about them in chemistry 2 years ago. There is the alpha particle, and there is the beta particle, and there are the gamma rays. These are Greek letters, alpha, beta, gamma. These two are particles with mass. This one is particles also, but they're photons. You know some things about photons. They travel at the speed of light. They're also considered electromagnetic waves. But all three of these things can be emitted. Now, we're going to take them one at a time, just cover a few basic things about them that you will need to know, starting with the alpha particles. Alpha particles, there's the Greek letter alpha. They are basically simply, each one is basically a helium nucleus. An alpha particle is the nucleus of a helium atom, which means 2 protons and 2 neutrons. That is an alpha particle. And, okay, and it has mass. It's the mass of 2 protons and 2 neutrons. It has a charge. See, it's positive. There are no negatives there. It's not a helium atom. It's a helium nucleus. Not very dangerous because it's just helium. If you're near a radioactive substance giving off lots of alpha particles, they're going to combine with some electrons in the atmosphere and just become helium atoms. Helium atoms don't really hurt us, but they are positively charged. They do have some energy. Their regular clothing will block them for the most part, so they're not really going to hurt you. If I was to write an equation, a nuclear equation for the emission of an alpha particle, it would be something like this. Here's a U, 238 and 92. U stands for uranium. That's the mass number, protons plus neutrons, but they're 92 protons. And this uranium nucleus with this many particles in it emits an alpha particle. Now the alpha particle has a mass of 4 and it has 2 protons. There it is. Conservation of matter, we already know what these numbers have to be. The uranium changes to something else. This is actually called a transmutation because trans means there's a change, and mutation, it actually turns into a different thing. After it emits alpha, it's no longer uranium. Why not? Because it had 92 protons and it lost 2 of them. Now it only has 90 protons. It had 238 nucleons total in the nucleus, but 4 total went away. Therefore, this number is now 234. And if you need to know what that is, which you probably would be interested, you simply look on a periodic table. And I have one right here. And maybe you can see that number 90 is thorium. Okay. TH. You can always look up the element on a periodic table. Nobody memorizes what number 90 is. But this right here is a nuclear equation, not a chemical equation. There's no chemical reaction here, but it's a nuclear reaction. Emission of alpha particle. You can see that you do end up with a new substance. It's no longer uranium. Now, thorium is also radioactive, and it would emit particles. And the idea is that particles would continue to be emitted until it turns into something stable. Remember, our whole point is that things that are radioactive are lacking stability, so they emit particles so that eventually they will become stable. All right, let's go to number 2. Number 1 was alpha, number 2 is beta. Do you remember, Nate, do you remember what a beta particle is from, I don't know, some science class you've had in the past? Beta particle, there's the Greek letter, capital beta. Nate, do you remember? You are correct. Wait, I don't know if he's correct or not. Do you, Kyle, think he's correct? Do you think he's correct because that's right, or you just think Nate's probably always going to be right? Both. Good answer. Beta particle is an electron. It's an electron. That's all. It's an electron. It comes shooting out of the nucleus. Maybe you remember us talking about this in chemistry, because I think we did, at least briefly. And I know Sophia is out of her chair right now saying, no, an electron can't come shooting out of the nucleus of an atom. Nucleus doesn't have any electrons. Sophia, sit back down. We're going to try to answer your question. Out comes this beta particle, which is an electron. Electron doesn't have any mass in terms of U's. Its mass is so slight, it's a whole lot less than 1 U, therefore it rounds off to 0. But it does have a charge of -1. This is normally the number of protons, but that just means it's the charge, because protons have a charge of +1. Well, the beta particle is -1. We would symbolize it that way. Now, back to Sophia's question, what was an electron doing there? Well, here's what does happen. A neutron splits into a proton and an electron. This will kind of make sense to you. Neutron is neutral. Well, if you put a proton and an electron and squeeze them together, that would be neutral too, wouldn't it? They have the same charge. Neutron, you probably know, has a very slightly greater mass than a proton. If you look up again those numbers on that chart on the first page of the chapter, yeah, neutrons are very slightly more massive, not much. They both round off to 1 U. But in terms of 7 significant digits, neutrons a little bit more. How much more is it? About the mass of an electron. Yeah. So this should make sense. Now, once this happens, the electron then leaves. The proton stays. The proton stays, the electron leaves. Well, what happens to the nucleus? It lost a neutron, but that doesn't give it its identity. It now has 1 more proton than it used to have. It's now number 93. All right, so let's write that nuclear equation. I have uranium, again, 238. Uranium's a good substance to use as an example. And this time it emits a beta particle, which we just talked about would have those numbers. So what is left? This mother nucleus, sometimes it's called the mother because it can emit things. Yeah. The mother nucleus turns into something different. It's not uranium anymore. This time it's going to be number 93. Now just look at the math. 93 and a -1, yeah, that's 92. Well, it's 0, so what number would be up here? It's still 238. See, the number of nucleons didn't change. 1 neutron was replaced by a proton, so the mass number is still 238. The electron left. So this has become element number 93, which is number 93, Neptunium, NP. Uranium turned into Neptunium by emitting a beta particle. You can see that when beta particles are emitted, the atomic number actually goes up one because a neutron turns into a proton. Whereas we saw earlier when the alpha particle is emitted, the atomic number goes down 2 because it loses 2 protons. All right, so this is the nuclear equation for beta emission from uranium-238. The third type of particle is the gamma ray. Now, all of these can be called rays or they can all be called particles because they're both. But this is number 3, the gamma. And I like to write gamma ray just because it is the electromagnetic wave. But realize this is photons, which we've talked about. All right, the gamma ray is a very high energy electromagnetic photon or photons. High energy because, remember, energy is HF from the previous unit. These electromagnetic waves have very high frequency, very high. If you remember the electromagnetic spectrum, radio is way down here on the low end frequency. Gamma rays were up on the high end frequency. Light is in the middle. Okay, I'm reminding you of the electromagnetic spectrum. Well, here's what was on the far right, which means the highest frequency, therefore the highest energy. These things have lots of energy. They can do great harm to a living thing. I should say, here, we're right, very harmful. Because there's so much energy, they can penetrate your clothing, your skin. They can go right to some organ inside your body and begin to burn it because there's so much energy in that photon. They are the most harmful. I don't think I mentioned beta particles. They're more harmful. Beta's in the middle. They're more harmful than alpha, but not as harmful as gamma. Beta particles are electrons that come out with a good bit of energy, so they can penetrate your clothing too and harm your physical body in some way, but they're not as bad as this. Okay, in terms of danger. If I were to write a nuclear equation for uranium emitting a gamma particle, 1 photon, what would its numbers be? Well, what is its mass? It's a photon. It doesn't have any mass. What is its charge? Remember, helium nucleus was +2. Beta was -1. It's an electron. What about a photon? Photons don't have charge. No photons have charge. 0. So, what did the mother nucleus turn into? It's still the same thing. 0, 0. It's still 92. It's still 238. It's still uranium. So, uranium does not transmutate simply by emitting gamma particles. It loses energy. See, what actually happens is a nucleus, you can think of it this way, the nucleus drops to a lower energy level. It's the same kind of conversation we had with the electrons in the previous chapter, where electrons would go to a higher energy level and drop back down and give off photons. Well, what happens here is the nucleus drops to a lower energy level and it gives off photons. And they're high energy, high frequency. All right. So The nucleus did lose some energy, but it did not lose any mass. It did not change the number of protons. I shouldn't have said it doesn't lose mass, because that's not true. But it does. Its mass number is conserved. Please notice in all of these nuclear equations I have put on the board, these numbers are conserved. The top numbers and the bottom numbers, the ones on the right must equal the ones on the left. That's true for the mass numbers, and it's also true for the atomic numbers. The numbers on the right must equal the numbers on the left. No variation to that. However, what about the mass? I'm going to pause this while I erase the board. All right, we're almost through it. Let me point out what happens with the actual mass. Here's our alpha particle. I wrote He this time for helium nucleus, but it's an alpha particle. So uranium gives off alpha, produces thorium. Okay, we talked about that a moment ago. Here are the actual masses. Actual masses meaning beyond 238. This is the actual mass of the uranium. This is the actual mass of that alpha particle. This is the actual mass of that thorium. And when you add this together, it's a little bit less. There is a mass defect in this reaction. And if you subtract the 238.0508 minus these numbers added together, which are 238.0462, you can see this is a little bit more than that, and the difference is 0.0046 U's. That's the amount of matter that was lost. That's the mass defect in this nuclear reaction. That means there's some mass that disappeared. Where did it go? Jack, where did it go? Yeah, it turned into energy. How much energy did it turn into? Well, if we take U's and multiply them by 931.5, we will get the amount of energy that it turned into. And I don't know what that is, or yes, I do. 4.3, if I round it off to 2 digits, 4.3 mega electron volts are emitted when just one alpha particle is released from a uranium atom. Therefore, all of the processes we've just talked about, alpha, beta, and gamma emission, there will be a little bit of mass that disappears. If you add up the masses on the right, it's less than the mass on the left. How much less? Find that out, and then convert that to energy, and you will see how much energy then had to be released in this process. That's why radioactivity does give off energy. It isn't just that particles are flying out, it's particles with energy. And that's how much. You can see that. There you go. That's how much. All right. We're out of time today. Your homework again is assignments C and D. Have that ready by noon tomorrow, which it would be Wednesday. And I will see you then. I love you guys. Take care.